A very good morning to one and all. Welcome to our presentation on microwave oven project. It is being presented by Sonia, Narendra Kumar, Keerthipriya and Himanshu. Myself, Keerthipriya, and I am going to present about overview of Emertxe systems. We are currently pursuing fourth year in Jawaharlal Nehru Technological University, Hyderabad. Let's move on to the contents. The contents are topics learned, overview of embedded systems, project requirements, interfacing, implementation of microwave oven, conclusion. During this internship, we have learned the topics about introduction to C programming, conditional loops and operators, arrays and pointers, functions and strings, introduction to embedded systems and microcontrollers, MPLAB XIDE and XC8, PiximLab, introduction to various peripherals of PIC microcontroller and interfacing various peripherals of PIC microcontroller. Overview of embedded systems. An embedded system is a specialized computer system that is designed to perform specific tasks or functions within a larger system. Unlike general purpose computers, embedded systems are optimized for a particular application and are often found in a wide range of devices and products. Example: microwave oven, washing machine, smart TV. Categories of embedded system. Embedded systems are categorized in ways based on their characteristics and functionality. They are standalone embedded systems, real-time embedded systems, network embedded system, and mobile embedded system. Standalone embedded systems are the embedded systems that operate independently and are not connected to a network or other devices. Real-time embedded systems are designed to respond to events or inputs within a specific time frame. Network embedded systems are connected to network, enabling communication and data exchange with other devices or systems. And mobile embedded systems are designed to be portable and are often found in handheld devices or mobile platforms. Real-time embedded systems. Real-time embedded systems are designed to respond events or inputs within a specific time frame. They are further divided into two categories: hard real-time systems and soft real-time systems. In hard real-time systems, missing a deadline can have severe consequences. These systems are commonly found in safety-critical applications such as automotive airbag systems or medical devices like pacemakers. Soft real-time systems have deadlines, but occasional misses may not lead to catastrophic failures. Example: Moon rover and multimedia streaming. Components of embedded system. Microcontroller or microprocessor. It is a central processing unit responsible for executing instructions. Memory. It includes RAM for data storage and ROM or flash for program storage. Input or output interfaces. Hardware for communication with external world. Sensors and actuators collect data from the environment and perform actions. Software. The program that defines the embedded system's behavior. Power supply. Provides the necessary electrical power to the system. Communication interfaces. Networking capabilities like Ethernet, Wi-Fi, Bluetooth, etc. if required. Requirements of embedded systems. Reliability, real-time performance, efficiency, low power consumption, security, and cost effectiveness. Challenges in embedded systems. Resource constraint. It has limited processing power, memory, and energy. Real-time constraints. Meeting real-time deadlines can be challenging. Software complexity. Developing and maintaining embedded software can be complex. Hardware-software integration. Ensuring that hardware and software work together seamlessly. Testing and debugging. Testing embedded systems can be difficult due to limited accessibility. Trends in embedded system development. IoT integration, AI and machine learning, edge computing, low power design, wireless connectivity, security focus. Embedded programming. Host. The host in embedded programming refers to our development computer or workstation. We write, compile, and test our code on the host before transferring it into the target device, which is a microcontroller. Target. The target is microcontroller or embedded system we were programming. This is where our compiled code will run. Cross-compiler. A cross-compiler is a toolchain that compiles code on a host computer to be executed on a target platform with a different architecture or hardware. In case of XE8, it's a cross-compiler because it compiles code of big microcontrollers on our host computer. Thank you. Now, I would like to hand it over to my friend.
Hello everyone, myself Sonia. I would like to tell you about the project requirements. They are MPLAB XIDE, XE8 compiler, and PICSIMILAB. In PICSIMILAB, we have other peripherals like PIC16F877A microcontroller, 16x4 CLCD, Matrix keyboard, timer 2 module, and tactile switch. Features of PIC16F877A microcontroller. It operates at a frequency of 20 MHz. It has a flash memory of 8 KB. It has 3 timers and 50 interrupts. It also has 5 input-output ports. External peripherals are connected to the microcontroller through these 5 input-output ports. Those are port A, port B, port C, port D, and port E. It is a 40-pin IC with a data memory of 368 bytes. The first peripheral we are going to discuss is about CLCD, that is Character Liquid Crystal Display. It is a kind of LED used to display the messages, most commonly used to display ASCII characters. It has two communication modes, 4-bit mode and 8-bit mode. It has 16 interfacing lines. The information given to CLCD can be both instruction or data. Depending on the RS pin, that is the 4th pin of CLCD, it decides whether the given information is instruction or data. That is, when RS pin is 0, it is considered as instruction, and when RS pin is 1, it is considered as data. Read-write pin of CLCD is always connected to the ground by hardwiring. That is, only writing is possible in CLCD. Pins from 7 to 14 of CLCD are connected to RD0 to RD7 of PIC16F877A as data lines, that is connected to the port D upper nibble. The second peripheral we are going to discuss is about matrix keypad. It uses tactile keys. In matrix keypad there are 12 keys, that is 4 rows and 3 columns. In this project we use matrix keypad to select cooking modes, time and temperature values. The port D from RD0 to RD3 are considered as rows. Port B from RB0 to RB2 are considered as columns. While coding, generally rows are output pins and columns are input pins. Depending on which row and column are connected to the ground, key values are selected accordingly. When no key is pressed, that is all release mode, all rows and columns are connected to the VCC. The next peripheral is timer. We have 3 timer modules, timer 0, timer 1 and timer 2. But for this project we use timer 2 module. It is a 16-bit module with a prescaler and postscaler. Timer 2 can be used for both read and write operations. It is cleared on reset. The input clock has a prescaler option which is selected by control bits in T2CON resistors. Timer 2 module has a 8-bit period resistor which is PR2. Timer 2 increments from 0 until it reaches the value of PR2 and then resets to 0 on next increment cycle. The next peripheral we are going to discuss is about interrupts. An interrupt is a communication process set up in a microprocessor or microcontroller in which an internal or external device requests the MPU to stop the process. Then the MPU acknowledges the request and attends to the request. After attending the request, it goes back to the processing where it was interrupted. Generally, interrupts are of two types, hardware interrupt and software interrupt. If interrupts are caused by the peripherals, it is known as hardware interrupt. And if it is caused by the code, then it is known as software interrupt. The hardware interrupt is again classified into two types, maskable and non-maskable. If interrupts can be disabled, they are called maskable interrupts. If interrupts cannot be disabled even if we wanted, they are non-maskable because non-maskable interrupts have high priority and they cannot be ignored. These non-maskable interrupts are again classified into two types, external interrupts and internal interrupts. If the non-maskable interrupts are produced by the external sources, then it is external interrupt, and if these are produced by the internal sources, then these are internal interrupts. The last one is buzzer and fan. Buzzer is connected to pin 1 of port C and fan is connected to pin 2 of port C. Thank you. Now I would like to hand it over to my friend.
Hello everyone, myself am Narendra Kumar. I would like to explain the implementation of microwave oven. Power on. On turning the microwave oven, the oven display needs to display the power on message. Cooking modes. There are 4 different types of cooking modes. 1. Micro mode, 2. Grill mode, 3. Convection mode, 4. Start mode. Set time or temperature. The oven needs to facilitate the user to input required cooking time or temperature. Warming. The user needs to warm the oven in case of invalid time or temperature input or the door is open during the cooking time. And the oven needs to display cooking time up message on completion of cooking time. Functional requirements. Post powering on the microwave oven, the CLCD character liquid crystal display displays the power on message which is followed by the display of 4 different cooling modes. Figure 1 depicts power on screen. Figure 2 depicts cooking modes. The first mode, the micro mode. On pressing key 1 in the matrix keypad, the micro mode is selected. The CLCD displays the power. CLCD prompts the user to enter the cooking time. Asterisk button clears the time. Hashtag button confirms the time and starts cooking. When timer starts, fan starts spinning. Key 4 of matrix keypad adds 30 seconds to the current cooking time. Key 5 pauses the cooking, both timer and fan. Key 4 also resumes the cooking. Key 6 ends the cooking. The second mode, the grill mode. On pressing the key 2 in the matrix keypad, grill mode is selected. CLCD prompts the user to enter the cooking time. Asterisk button is used to clear the cooking time. Hashtag button confirms the time and starts cooking. Convection mode. On pressing the key 3 in the matrix keypad, convection mode is selected. CLCD prompts the user to enter the cooking temperature. Asterisk button is used to clear the temperature. Hashtag button confirms the time and starts cooking. Oven starts preheating with the given temperature for 3 minutes, following which prompts the user to enter the cooking time. The first figure depicts set time display, the second figure depicts preheat display. Start mode. On pressing key 4 in the matrix keypad, start mode is selected. Cooking time is set to 30 seconds and the cooking starts automatically. Features of PiximLab. Firstly, what is PiximLab? PiximLab is a software simulation tool primarily used for simulating and testing microcontroller-based electronic circuits. It is particularly popular for simulating circuits that involve PIC microcontrollers, hence the name PiximLab. Users can design, simulate, and debug electronic circuits that incorporate PIC microcontrollers and various electronic components such as sensors, LEDs, and motors. From here, my friend Himanshu will continue about the futures of PiximLab. Thank you.
A very good evening to one and all. Myself Himanshu, and now I'm going to continue this presentation by talking about the features of PiximLab. So let's talk about the features. The simulation feature is designed to simulate the behavior of PIC microcontroller, allowing users to test and debug the code in a virtual environment. The peripheral simulation often includes models for various peripherals such as LED displays, LCDs, motors, sensors, and other components commonly interfaced with PIC microcontrollers. It also has an additional feature which helps the user interface. It typically has a user-friendly interface that enables users to interact with the simulated microcontroller and peripherals. This includes tools for code editing, debugging, and monitoring. It also has a code development support which facilitates code development and compilation. The real-time simulation is really a boon for PiximLab. It aims to provide a real-time simulation capabilities, allowing users to observe the execution of the code as if it were running on a physical environment. Now let's talk about the architecture of PiximLab. This thing is a 4x3 matrix keypad, and these are the two relays which are connected to two different ports. This is a fan and this is a buzzer, which is an electronic component that generates sound when an electric current passes through it. And these are the two push buttons, and these are two sets of two arrays of LEDs. This is named as port D and this is named as port B, and this is a regulated power supply, and this is the reset button. And these push buttons, these are simple mechanical switches used as input devices. and this is the 16 by 2 LCD display, and these are the 4 displays that are available in dynamic mode. Now let's talk how you write a program in MPLAB XID and load that hexa file into this SpecSimLab. So this is the MPLAB XID where you generate where you write the program in C language, and these are the hexa files that are generated. These are the header files and these are the source files. So this is the hexa file that will be generated post building this code. You have to load this hexa file into this SpecSimLab here. After loading, I'll explain you why this is named as why this is written as 16 into 4. 16 means characters and 4 means you'll get the display in 4 different lines. Just a minute. Now this display will be shown in 4 different lines. Yeah, these are the 4 different modes. Micro mode. The first mode is micro mode. Second is grill. Third is convection, and the fourth is star. So by pressing the first button, you'll get the micro mode. The power is given as 900 meters, and now you'll get a chance to set the time. This mm is for minutes, this ss is for seconds. Now I'll be setting a random time for 11 seconds. Or some other number, 12 seconds, and I'll be, this hash is for enter, and this hashtag is to clear. Now these 4 is to start or resume, and 5 is for to pause. I'll show it by pressing 5. See, the time has been paused. Again, to resume, I'll press 4. To completely stop, I'll press 6, and the simulation has to stop. Yeah, it has been stopped, and again it came back to the initial screen. And I'll explain you the convection mode. You can set the temperature in the convection mode. I'll set a random temperature of 150, and I'll press the hash to set it, and this is the preheating time. It's a default for 18 seconds. And you can also in this way you can set all the 4 modes and see how it's working. So that concludes our presentation. Thanks a lot, Emertxe, for giving us this opportunity. The last 2 months has been really productive for us. We really learned a lot from this internship, and we hope to be a part of your esteemed in the near future too. So thank you. Thanks a lot.